Welcome to the 11th lecture of this course. In earlier lectures, we have seen the first tool, Smith chart, which microwave engineers use very often, and with that tool we have also seen how to measure impedance, and we have solved various problems for impedance matching. We have seen the design of impedance matching network. Now, in this week, in these 5 lectures, we will try to see the second tool that microwave engineers use, which is called S parameter or scattering parameter. Now, to kickstart that discussion, the first lecture will see voltage and current concept at microwave frequency. Now, at lower frequencies than microwave frequency, we know that the circuit dimensions or components that are used in a circuit, electronic circuit, their dimensions are quite less than wavelength in low frequency, because low frequency wavelength is quite large. So, typically in kilohertz up to megahertz frequencies, the circuit dimensions that we use for various resistors, transistors, diodes and various amplifiers, etc., that we build from them, their dimension is much less than wavelength. That is why the phase difference between 2 points in the line for a voltage or current wave, that is not much, and that is why we can uniquely define the voltage and currents at low frequency, and we assume that there is no wave type of thing there, though inherently there is wave, but at low frequency wave. So, voltage and currents obey the form of Kirchhoff's law, Kirchhoff's voltage law and current law, so that unless and until a component is encountered, the voltage and current do not change. But actually for a wave, definitely the voltage and current change as we move on. So, we have negligible phase delay between 2 circuit points at lower frequencies, and also we can use 2 conductor transmission lines like coaxial lines in low frequency, and in 2 conductor lines it is very easy to define the voltage and currents. So, uniquely. Also in low frequency, the fields that are transmitted through those 2 conductor transmission lines, they are mainly transverse electromagnetic type, or even if not transverse electromagnetic type, they are quasi TEM we call. That means almost like TEM, or for all practical purposes like TM. That is why the solution of Maxwell's equation at lower frequency, they also, for electrodynamic cases also, they are quasi static. That means something like electrostatic or magnetostatic type of solution. So, at lower frequency, the whole thing, though dynamic, though field based, though wave based, but their solution appears to be like the electrostatic or magnetostatic cases. So, that voltage and current definition suffice. But at higher frequency, obviously that is not the case. There we need to consider the non-TEM type of propagation. Maxwell's laws get solved there by various modes, that is why power gets transported by various modes, and we will have to solve those problems with the help of Maxwell's equations and boundary conditions. But in reality, though Maxwell's equation and its solution gives us all the information about the electric and magnetic field throughout the whole universe, you can say, and they are very exact, but always in even in high frequency design, microwave frequency circuit designs, we do not require so many information. If we look at our practical need is always terminal based. You know, a complex design problem generally we solve by considering or breaking the whole problem into several parts, and that is why we try to resort to block diagrams, and where a sub block, its characterization first we do, then we design that block, then we interconnect that block, and hence in practical cases we want to know at a set of terminals which are generally the ports of the sub blocks, there what is the voltage or what is the current going into one port or coming out of one port of that block, what is the power flow through that block, what is the impedance across those port terminals, and then we interconnect those terminals to connect several such blocks. If required, we modify their impedance levels, etc. And exact electric field and magnetic field description at all these points inside the block is not always necessary. So, engineers, we try to find that can we have some voltage and current concept defined at microwave frequency. But one problem of this high frequency thing is here the transport mechanism or the power that gets transferred through the medium, that is generally in the form of waveguides, which are a single conductor, which are not two conductor, because two conductors becomes lossy at higher microwave frequencies. So, single conductor does not support a transverse electromagnetic or quasi TEM type of waves. So, field here is non-TEM, mainly in the form of various combinations of transverse electric and transverse magnetic modes. And in a single conductor like waveguide, it is very difficult to get two terminals to define voltage or current. For voltage, you know, you require two terminals, so that we measure the potential difference. We are not bothered so much about the absolute potentials, the potential difference. So, for that we require two terminals. Similarly, current, if it enters to one terminal, it returns to another terminal. So, it also requires two conductors or two terminals to get it defined. And obviously, the characteristic of the network is the impedance. So, if voltage and current, they are non-unique, because here what happens due to wave propagation at various points, we have various voltages and current. So, impedance is also non-unique at high frequency. Now, the endeavor is, can we make, in spite of this difficulty, in these same waveguide type of cases, single conductor cases, can we in an equivalent way define unique voltage and current? Because if we can, then the instead of field theory, we can take the help of wave theory, obviously distributed theory. So, the circuit theory in the form of transmission line, that theory we can take the help of, and so our exact field solutions, which is a vector solution, three-dimensional solution, that will become much more easier. So, the question is, can these terminal quantities be made unique? Now, obviously, phase delay is unavoidable at this high frequency, as I said, that here, since we are very high end of frequency, gigahertz sort of frequency or several megahertz of frequency, several hundreds of megahertz of frequency. So, even a small length that adds to quite good amount of phase. So, we cannot avoid the phase delay. and obvious that is why here voltage will be in the form of voltage wave. We will have to find out how much it is going across a component. So, voltage in the form of voltage waves will exist here, current in the form of current waves will exist here, power also we describe in terms of power waves, as you have seen in the case of impedance matching we have shown power waves. And at the port, if we very precisely can define ports, that means on a terminal plane, if we fix that terminal plane, then it appears that we can have a try to define port voltage and port current, and obviously if we can do that we can get port impedance, but it can be due to the non-uniqueness of the solutions, it can be done in various ways. So, what is the best possible way by which we can define voltage and current? If we can do that, then we can do impedance matching and other design things. So, let us see first, let us see a two conductor transmission line, which is the coaxial line when it is extended up to gigahertz, up to gigahertz, nowadays even to 10-20 gigahertz it is used, it is modified. A very good designed coaxial line nowadays can work up to 20 gigahertz also. And this in this picture you are seeing that if we have two conductors, one is positively charged, another is negatively charged, and obviously there will be electric fields and magnetic fields between them. Now, quasi-static transverse field, as we said that if we have quasi-static field in two conductors, generally we have quasi-static type of field. Also other non-TEM waves also propagate through them, but if we make the quasi-static approximation and then the line integral voltage we know is the line integral of electric field, and generally the unique voltage definition is from negative to positive. That is why you are seeing from positive to negative the conductor, if we go, if we take the line integral of the electric field, that is voltage. Now, in case of two conductor line, this voltage definition is unique. Similarly, we know that the closed line integral of magnetic field gives us current. So, here the terminal current that is flowing on positive conductor, if we can have that current uniquely defined for any contour closed path enclosing positive conductor, then we can define the ratio of voltage and current so defined as the impedance, and this is basically the realm of transmission line theory. But let us see rectangular waveguide. Rectangular waveguide as dominant field distribution as TE10, it is a non-TEM mode, and electric field, the transverse electric field, it has only one transverse electric field, it is along the narrow dimension of the waveguide, that is generally we called y direction. The expression is given, the variation is along x, the variation is shown in the figure, and it is a sinusoidal variation. The wave is propagating in the positive z direction. Now, from that, if we have that voltage is equal to the line integral of this, we come across the expression shown here. Obviously, this V, the voltage depends on which path we are taking to integrate, and also the values of x and y that we are traversing on the way. So, that is why we are saying, suppose we take the middle path, that is x is equal to a by 2. At the middle, if we take that integration of y from y is equal to 0 to the top wall y is equal to b, we will get some value of that line integral, and that obviously is not equal to the thing if we do at, let us say, x is equal to 0, that means on the narrow wall. So, unique voltage, current, impedance, these are not defined in case of a single transmission line. So, what is the way out? Fortunately, microwave researchers have come up with ways to tackle this problem. They say you can still define voltage and current, but obviously for a particular non-TEM mode. That means, for T10 mode there will be a voltage current definition, for T20 mode there will be another voltage current definition, for TM10 mode there is another current voltage and current definition, etc. Now, there are 4 guidelines. The first is, you know every mode, you know what is the transverse field. So, voltage should be defined proportional to the transverse electric field. This is the first dictum. The second one is, the current also should be made proportional to transverse magnetic field. Now, obviously, this proportionality constant can be many things. So, this is not uniquely said, but then 2 more conditions are imposed on these 2 to make the whole thing very unique. That one thing is, the instantaneous power flow should be equal to the product of voltage and current, and the ratio of this voltage and current, that should be defined as an impedance, and there are 2 choices. That impedance so defined can be made equal to the wave impedance, because every mode has a modal impedance, which is the ratio of the transverse electric field to transverse magnetic field, so that the power can propagate to z direction, that is called z w or wave impedance. So, you can make that impedance so defined from voltage by current either as wave impedance, or you can normalize that. These 2 choices are existing. So, if this is done, then at a terminal plane we can uniquely define voltage and current. Obviously, voltage and current will propagate in the z direction in the form of a wave, but the terminal voltage and current, they will be unique. So, that is why let us say that an arbitrary waveguide mode, its transverse component of electric field will in general be a function of x, y, z. So, that can be written as the eigenfunction E x y into one positive going wave e to the power minus j beta z, another negative going wave e to the power minus e to the power plus j beta z. We are calling j beta, that means we are assuming it is lossless. If it is not lossless, it should be gamma z and minus gamma z, the propagation constant. Similarly, the transverse magnetic field also can be written like this. This is the breaking of any waveguide, any electric field into various waveguide modes. Now, we know that electric field eigenfunction and magnetic field eigenfunction E tilde and H tilde, they are related through the modal impedance Z omega. This is the field theoretic point. Now, to make equivalent voltage current, what we do, we write V z as a positive going voltage wave V plus e to the power minus j beta z, and obviously also a reflected voltage wave V to the power minus e to the power j beta z. Similarly, the current wave also we break into two parts, one is incident wave, another is reflected wave. Remember that incident and reflected wave, there is a negative sign between them because of power propagation direction. Now, see that the guidelines for defining equivalent voltage current, the two first points are the equivalent voltage is proportional to the transverse electric field. That is why we are writing E t x y z, that should be written as V plus by C1, C1 is a constant. Obviously, the eigenfunction will be there, but other parts we are writing as V plus by C1. Similarly, the magnetic field is made proportional to the current. The constant of proportionality in this case is C2. Now, we are forcing the power flow condition, that instantaneous power flow should be the product of voltage and current. So, if we assume time harmonic fields, that is sinusoidal fields are one form of time harmonic field e to the power j omega t, then we can also define an average power wave, power flow. Now, the incident power flow can be written like, we know it can be expressed as the Poynting vector, surface integration of Poynting vector. So, half comes from that e to the power j omega t, it is a sinusoidal variation. Any sinusoidal quantity, its average is half. So, half E cross H star, that is a Poynting vector, it is a power intensity, power flow per unit area, that dotted with the ds vector. So, that expression we wrote. Finally, we also wrote it as, we know already we have made those A plus things as proportional to voltage and current. So, in terms of voltage and current it is written. Now, the demand is instantaneous power flow should be equal to V I. So, in terms of complex things, the average power flow should equal to half V plus I plus star. So, the first equation, top equation we have written in terms of field, and the second equation that it should be equal to this half V plus I plus star. So, these two if we made equal, then we get one condition on C1, C2 as shown that their product is certain things depending on the eigenfunction. So, depending on the wave's modal variation and the geometry of the guide, this can be evaluated the right hand side. Also, impedance should be equivalent, that means the Z naught, that is equal to E y plus by H x plus, which turns out to be E by H, that should be also equal to V plus by I plus, or ratio of V minus by I minus. Now, if we made that, again we said there are two choices, C1, C2, ZT, in this case it is ZT because we are talking of T10, or you can make C1 by C2 is equal to 1. We will solve problems later in the tutorial, we will take the second choice and show you can also take the first choice. So, generally the field can be described like this, that transverse field E t now can be described in terms of those equivalent voltage and currents as V n plus by C 1 n, as you see the sum of V n plus and Vn minus. Similarly, the transverse magnetic field also can be written in terms of equivalent currents In plus and In minus. C2, Cn are there. You can solve for the values of C1 and C2 by enforcing the power equivalence and impedance equivalence. Those two unknowns, two equations. So, you can find out their values and those values you can put. So, various modal things, as there can be various modes possible, particularly near the discontinuity etc., or near the excitation when we are very near to the source or very near to the load or very near to any discontinuity. The instead of a single mode, various higher order modes also are present. That time we can write that in form of various modal voltage and currents. This is the description, and this completes that how you can define equivalent voltage and current in microwave frequencies. Obviously, this is a dynamic problem, electrodynamic problem. At higher frequency, it is not as simple as the low frequency voltage and current and Kirchhoff's current law, Kirchhoff's voltage law and current law type of thing, but it can be done. So, now every mode has its own counterpart of voltage and current. So, that is a good step forward, that now we can attempt using transmission line theory to these, so that instead of solving Maxwell's equation, we can get away with lesser information, but as a practical engineer we are always not go for all exact information things, but the practical useful things. So, this will be shown to lead us to an useful concept, which is the second tool, which is focus of our this series, that scattering parameter, in the next lecture.